All right. So, today in class, you actually should be taking the Unit 2 test, so good luck on that. But starting tomorrow, we're going to be getting into Unit 3, which is about acids and bases. Um, since Halloween's coming up this week, and Halloween's one of my favorite days of the year, just using some Halloween-oriented questions here. So my favorite piece of candy, let me find a picture of it and post it on here, is big drum roll here. Sorry, that was way more took way longer than I thought it was going to, but my absolute favorite candy is Butterfinger. So usually, like, you don't often find it in the bags that have a bunch of different things. So I usually end up buying a bag of Butterfingers separate for myself and then give the rest of the candy to trick-or-treaters. Okay, so acids versus bases. Some general characteristics. What I want you to do before continuing on with the video is see if you can come up with at least two things that you already know about acids and bases. Okay? Some of this stuff we might talk about in this lesson, some of it might be in the next one, but I bet there's stuff you already know. So pause the video for a second and try doing that. Since this isn't live, I don't have anybody here to put it in there. So hopefully now you've come back and you've unpaused the video, and this is the differences we're going to focus on in this lesson. Okay, so acids, when food has an acid in it, it usually makes the food taste sour. Okay, like a lemon. Lemon is a very acidic fruit that's very sour, right? Any citrus fruit has an acid in it, and that tangy sourness to the citrus fruit is what how you can tell the acid's there. Okay, acids can make, if it's a relatively weak acid, it'll make your cut, like if you get it on a cut, it'll sting. If you ever have gotten lemon juice on a cut. Or even, if you're squeezing oranges or something like that, that can sting too. If you have a strong chemical acid, it can actually cause a near immediate burn to your skin. Okay, so food acids aren't so bad. They're relatively weak in terms of things, but strong acids that you might use in a laboratory setting can definitely cause some damage to your skin if you get down there. So if that happens, you'd want to wash your hands right away. And some of our labs do involve hydrochloric acid, which isn't the worst one in the world, but it is a very strong acid. And if you do happen to spill on yourself, make sure you clean it off right away. Acids react very strongly with metals. Okay, you get a lot of heat coming off, some bubbling and some fizzing, because the metal makes a salt with the chlorine and, say, a hydrochloric acid, and then gives off a gas. Okay, so you can find acids in citrus foods. Soda pop has a fair amount of acid in it. Then stronger acids that you'll probably want to be familiar with, because you might just see them referenced in course materials, is hydrochloric acid, or HCl. Okay, that's what's in your stomach. So that's why if you're having heartburn, it kind of burns, because that's the hydrochloric acid getting into your esophagus. And then a really strong laboratory acid is sulfuric acid. And that one is definitely not something to trifle with. Bases, on the other hand, bases typically aren't found in food, but the substances that they are found in taste bitter. And our bodies are programmed to taste bitter most often when something is poisonous. Okay, so bases wouldn't be something you want to drink. All right, so it's a good thing that our body recognizes that as being bitter and kind of off-putting, and we don't want to eat it. Bases, if you feel them, like if you have sodium hydroxide, it feels kind of slimy. All right, now strong bases, just like strong acids, can cause burns. They're usually not as quick reacting as the acids are, okay, because bases just don't react with things as quickly as an acid does. But if you do, again, we have sodium hydroxide in some of our labs, you get it on, you wash it off your hands right away, okay, because if you leave it on there, it will eventually cause a burn on your skin, and it's not fun. And then household things where you'll find bases are usually in cleaning products, right? Most cleaning products are basic. Ammonia is a common household cleaning item that is a base, and sodium hydroxide is one of the main ingredients in things like oven cleaner. Some of those really kind of harsh smelling, strong cleaners oftentimes have sodium hydroxide in them. Okay, so acid and bases, we care about them separately, but they also do what is called a neutralization reaction. Okay, so when you have an acid and a base, generally speaking, it's not always a good thing to have a strong acid or a strong base. So to counteract it, you have to neutralize them. So if you combine acids and bases, they essentially cancel each other out. Okay, they create a product that has qualities that are entirely different from an acid or a base, and we call that product something neutral. Okay, so the name for this kind of reaction is a neutralization reaction. So it's a combination of an acid and a base. And then more often than not, neutralization reactions involve your acid and base combining to make a salt. So something that is a metal ion combined with a nonmetal anion, okay, and water. So for example, we have sodium hydroxide and hydrochloric acid. All right, these are the acid and the base are dissolved in water, so they do disassociate, or the ions come apart. So when that happens, the OH minus and the H plus from the base and the acid respectively combine to make water, and then the sodium and the chlorine combine to make a salt, sodium chloride. All right. So, and again, remember from last block, salt doesn't mean just sodium chloride. Any ionic compound is called a salt. Okay, so if you combined NaOH with hydrogen fluoride, you make sodium fluoride, which would also be called a salt. Okay. Some types of acids and bases. So the definitions of acid and bases have been changing over the years. The first person to kind of put a definition down was Svante Arrhenius in the 1880s, right? And this is honestly where most classes start out and where you kind of start your learning. So that an acid is going to give off a hydrogen positive ion, an H plus, and a base is going to give off an OH minus. Okay, so if you look back on the last slide, we've got our base has the OH minus, our acid has the H plus. And that works for a lot of acid and bases. It doesn't work for all of them, because ammonia is a base, but it has no OH to give off. All right, so took a good 42 years, but eventually we started to make this definition a little less specific so that it could incorporate all of the acids and bases. So the first group of people to do that was Johannes Bronsted and Thomas Lowry. All right. And what does stay common among all acid and base reactions is the presence of that H plus. Okay. And they defined it as an acid is something that can donate the H plus or give the proton. Okay, H plus is sometimes shorthand called a proton. All right, and then bases are able to take them. All right, so that gets a little tricky and a little kind of confusing, especially when we get a little bit further and we talk about what water does. So in another year later, Gilbert Lewis defined this just a little bit more generally. Okay. Whereas acids can accept electrons, right? Because they're going to give away something positive, which means they gain an extra electron, right? So they're not letting hydrogen take its electron with. And bases donate those electrons, okay? Because they're going to be the ones that grab that H plus, and they're going to donate their electrons in order to cancel out the charge, right? Really, you don't need a huge, strong understanding of this. Just make sure you can tell these up, maybe make a chart, be able to tell these apart. Speaking of a chart, that's what I did here, okay? So this was meant to be a review for someone who came in and was in class with me, but um, what I would do is I'd pause the video and see if you can sort this yourself. Okay, so like making OH ions, OH minus ions, that should be base. All right, so see if you can organize them into what should go where, and then we will start the video back up and I'll show you what it should be. All right, so I need to move this. There's the key. If you have it in a different order than this, that's fine. There's no specific order that things need to go in. All right, it's just for acids, you have to have that they can cause a burn very quickly. All right, they taste sour. Examples are hydrochloric acid and sulfuric acid. They donate protons, make H plus ions, accept electrons, and react with metals. And then bases are slimy feeling, they have a bitter taste. Common examples are sodium hydroxide and ammonia. They accept protons, make OH minus ions, and donate electrons. And last, they don't react with metals. Okay? So the last part is when you get down here, these go along with somebody's name. All right? So I want you to think about it. You need to rewind a little bit, but make sure you can also, if we talk about, say, hydrochloric acid donates a proton, who would have made that comment or something like that, you should be able to identify the description of the acid and the base by the name of the person who described them that way. Okay, so again, go ahead and pause the video and see if you can correctly match up these three names. And then you can start it back up and I'll show you which should be correct. So now that you've tried, hopefully you have it in this order. First one is Bronsted and Lowry. Arrhenius was the one who defined it as by what ion they gave off, and Lewis is the one who made it the least specific by just saying accepting electrons and donating electrons. Okay, so this is enough to get you through 3.01 and 3.02, and hopefully I'll see somebody in class next time. I know we got AZ Merit going on, so that's probably why I've got people missing.